Okay, for this next example, I really want you to have tried some easier examples before jumping into these beams that are at an angle. A lot more complicated question, there's no doubt about it. So do some easier questions first and then come to this one. So in this question, we are wanting to find the tension in the horizontal cable. So the tension that's acting along this cord. What direction is that tension acting? Well, from the pole's perspective, the pole is feeling a pull on it right here, and it's going towards the vertical wall. Okay, now I'm going to actually draw my diagram separately because there's just too much stuff getting in my way, and we want to have nice clean diagrams. Okay, so there's my pole. And I'll put that tension on my pole right here. All right, so tension. And I know that this is my 40 degrees right there. Now, what other forces are acting on this pole? Notice that there's a sign hanging from the end. So let's draw a weight vector acting straight down. And I'm going to call this capital MG, big MG. All right. There's another weight acting on this pole. Notice that the pole has a mass of 25 kilograms. So don't forget the mass of the pole. It is often forgotten. So if you do forget the beam or pole's weight, it's a rookie mistake. So cut yourself some slack. And there is one other force here. Look at what's happening down here at the hinge. This pole is pushing into the wall. There's a push. And so what does the wall do back onto the beam? It pushes back. Okay. Now we don't know what angle the pushback is at, but for the time being, I'm just going to put it randomly like this. And you could call this the force from the wall or the force at the hinge. You could use an H for hinge. It doesn't really matter too much. Okay, those are our forces. Now let's start labeling some of our distances. So the pole itself is 6 meters long. So I'm going to, this is how I like to do my distances. I like to get them the heck away from the diagram. Okay, and then I'm just going to draw my first distance to here. And I'm going to call this my D1. Okay, I'm going to have another distance here. And notice that this is going to where the tension is acting. I'll call this D2. And there's going to be one more distance. And maybe, yeah, I guess I'll throw it in here. To here. Ooh, not the straightest line ever, but that's okay. D3. And that's the force to there. Why aren't I doing a fourth distance? Well, because I'm going to pivot through the wall force, and I'm pivoting through there because I'm not being asked to find the wall force. I don't know anything about the wall force. So if I pivot through here, this entire force, even though it exists, will have no torque. Okay, so this is my pivot. And notice I'm doing all of my distances from that pivot point. So 3 forces, 3 distances. Okay, now the next thing that we have to do with our diagram is break up any force that isn't at a 90-degree angle to the beam into components. So let me just grab another color. I'll start with the beam's weight, and we're going to turn it into a perpendicular component and a parallel component. Make sure those meet at 90 degrees. I'm not going to label the parallel component because it doesn't factor into my torque. Okay, if you want to label it, have at her. Here I have big MG perpendicular, and then we're going to do a 90-degree turn into my parallel component here, and there's my 90 degrees. Last but not least, I have my tension. There's coming straight out. Some of the tension is acting perpendicularly to the beam. So there's my T perpendicular. Do a 90-degree turn, and there's my T parallel. Now, if I'm looking for my L's to find my torque, it's going to be this force times this distance. And then we're going to do, my other torque will be this force, T perpendicular, times this distance. And last but not least, I'm going to have a torque from big MG perpendicular times this distance here. Okay, so we want to look at the L's. All right, so the only other thing that I personally prefer to do is I like to do a list. So I'm going to pause the video and make my list. All right, here's my list. I've got all my distances labeled. The one that I had to figure out was D2. Notice that there is a 1 meter mark given on the sign here. So we're 1 meter short on D2, so that's the 5. And D3, we assume the center of mass is right in the center on questions like this. It's a uniform pole, right? When it says uniform pole, it means the mass is constant throughout the pole. Now that I have a really nice looking diagram, oh, wait a second, I forgot my angle. Let's put in that 40 degrees. So that 40 degrees has to get into all of these triangles here. So let's use Z rule. We'll put it up here. I'm going to use a Z rule and put a 40 degrees down here. Okay, see, there's my Z. And then using some basic geometry, you're going to put your 40. You can figure it out to be in the top angle there. Okay, now let's go to our first principle step. Our first principle step is that we're going to sum up all the torques and let them equal to 0. What this means is that all of my clockwise torques are going to be balanced or equal to my counterclockwise torques. Now, which ones are clockwise and which ones are counterclockwise? It looks like for both of them, the weights, I'm going to have clockwise. And it's not a bad idea to actually label these little twists on your diagram. Okay, so this weight is going to twist the pole downward, so it's going to twist it in a counterclockwise, or pardon me, a clockwise, my bad. And it's only the tension here. This tension is going to be my, hold on, I did my arrow in the wrong way. This is going to be going this way in the counterclockwise. So I have 2 clocks and 2 counterclocks. All right, so I'm going to come down to here now, and on the clockwise side, it's the 2 weights. So this part is actually quite fast because of our nice clear diagram. It's going to be the force mg times the distance, and it looks like that's D3. And then I have another clockwise torque right here. Here, I'll highlight it. I'm going to do this torque now. So that's going to be big MG perpendicular. And what's my D there? D1. And that's going to be equal to all of the counterclockwise torques. And there's only one. It's from the tension. So let me grab a different highlighter here. There we be. See that L there? I'm going to turn that into a torque. That's going to be the perpendicular component of the tension times D2. Okay, let's put our trigonometry. Hats on for a second here. So MG perpendicular. This is adjacent, and this is another adjacent. So adjacent hypotenuse cosine. I'm going to be writing baby mg cos 40 d3 plus big mg cos 40 d1 is equal to the tension. Now look at the tension here. T perpendicular, tension perpendicular is opposite the 40. Opposite hypotenuse is sine 40. And don't forget that D, D2. Okay. Many of you are substituting in your numbers now. Please don't. Just don't. Okay, push yourself to do the algebra first and then do your substitution at the end. Okay, if you have to put the numbers in right now, I won't take marks off, so don't worry about that. But I'm just looking towards the future for you, where you will be forced to do this. For some of our problems, you won't be able to finish the problem unless you do the algebra first, because what you're going to find is that things that aren't in the list, that aren't given to you, but you think you need, they'll cancel out if you do your algebra first. So yeah, can you just trust me on this? Do your algebra first. Okay, and all divided by sine 40 d2. Okay, I'm going to do my substitution and I'll be right back. Okay, so I did a little bit more than the substitution. I finished it off. It's really important right now, folks, for you to pause the video, write it all down, and please, can you take this calculation and see if you can put that into your calculator and get an answer in one step? Please. Stop writing down little baby steps along the way. Just learn how to use your calculator and be a hero. And I really love it giving people calculator lessons if they need them. Okay, like I can help you learn how to use your calculator efficiently if you are worried that you're going to make a calculator error. Okay, but this should be going into one button push, you hit equal, and you get your answer. Okay, so please practice the calculator part. Now there is a second part to this question that hasn't been written down. Sometimes in the questions, they want to know what the wall force is. What is the wall force? So what I want to do right now is actually put the wall force back in and just talk about how you would find what that value is. Okay? When we're finding the wall force, we want to go to the other conditions for equilibrium. And what I mean by that is we're going to look at the sum of all forces in the x direction and y direction. And so if I take Fw here from the wall, I'm going to break it up into Fwy, do a 90-degree turn, Fwx. Okay? And maybe for the purposes of this discussion, I'm just going to erase some of the stuff here. Just going to erase some of that. Oops, don't need the 40. Oop, okay. I will put that arrowhead down though. And I've erased all those pieces because those pieces were good for the rotational equilibrium. But when we're trying to find Fw, we just need to figure out the x and y components of Fw, and we're set, right? Because we can use Pythagorean theorem to get the rest of it. And when you see the force diagram like this, kind of stripped down, take a look at Fwx. Since the sum of all forces in the x direction has to equal to 0. Take a look at that. Those two forces, they're not drawn the same length, but they have to equal each other, right? So you can add this to below your notes if you like. I'm just going to do it right here on the side. But to find Fw, we're going to sum all the forces in the x direction and let that equal to 0. And so that means that Fwx is equal to tension. Wait a second, didn't we just find tension like a second ago? We have our tension. So we actually know what FWX is. It's this FWX, without doing any calculations, must be 679 point, I think it was 728. I'd have to double check. Newtons. Okay. And then let's look at the y direction. FWY is vertical. And oh, look at that. I've got baby mg and big mg. Those are the only vertical forces that are acting. So guess what? We can do one more little realization for this other condition of equilibrium and say that F sum of all forces in the y direction equals to 0. Therefore, FWY must sum to the sum of baby mg and big mg. And we know the weights. We know both of those. So that means we know the y component. And we also know the x component. And a quick Pythagorean theorem will get you that FW. And just for completion's sake, you could just say, I'm not going to calculate it. It's kind of boring. The calculation is boring. Pythagorean theorem is kind of boring, although it's very useful. You're just going to use it because you're going to have the numbers. You can get the values for these from here and here. Okay, so that's the question. All done for you. If you needed to copy this down a little bit more, I can maybe shrink this down. All right, and that's it. Okay, good luck. Happy torquing.